Hi everyone. Um, so this is our live stream. I'm going to try to do it over the uh, both classes. That's a 3-hour span. I don't know how much stamina I'll have, but I'll go through some problems with you. And if you look to the side of the page that you're watching this in, you should see where you have a text chat. You can just text any questions that you have in there. Otherwise, what I'm just going to do is I'm going to go over the problems that are online, and I know the solutions are online too, but I'll do variations on them. And if you have any questions about like how they're done, or you didn't understand my solutions, or you want more problems of the same kind, I mean, you just put that in the chat, and I'll be happy to accommodate you. Um, there is a 30-second delay, and so if you chat something and I don't see it, you wonder why did he just look at the chat and he didn't respond. It's probably because I didn't see it yet. Okay, like I said, there's a 30-second delay. Okay, so let me just start off by saying what's on the final. And I thought about this, and I normally would do a comprehensive final, but it's pretty hard under these conditions to, have the kinds of review sessions that I would have liked to have had in order to cover everything. And so, um, unfortunately, I think the best thing to do is to just do a test which covers the material that we did since the last test. And if you take a look at our Moodle site, so you're 112, even 111, sorry, 102. If you guys, if there are any 102 in there, it's the same topics. It's just that the 102 have a little bit more calculus than the 112. Okay. And I won't cover the 102 today, of course. So if you just scroll down, okay, there's electricity and magnetism, okay, and so all of this material will be on there. All right, and as well as optics. Optics is a shorter topic. There was only one video on that, but there were quite a few videos on the electricity and magnetism. And I've got the usual problems there. So I've got, an assignment problem and then solutions, and then I gave some extras. I don't have the solutions up yet, but I will soon. Okay, and also some problems for magnetism, and I don't have those solutions up yet, but I will. Okay, and if I do any extra problems today, I might put those up as well. Okay, and then of course, down here is all the material, and I'll point out which lectures you should look at before the final. All right, let me look in the chat if there's any questions to start with. Just a bunch of people saying hi. Hi everyone. All right, well let's begin here. So let's start off with just plain old electricity, and let's take a look at the assignment questions there. And how many do I have? I have 7. Oh, and there can do more than 7. Just very quickly, let me remind you of what we did in just for electricity. And we started off with static electricity, that is, charges which are not moving. And we started off with forces between charges that are not moving. And that was governed by Coulomb's law, which looks a lot like Newton's universal gravitational law. And then we switched from that to electric fields. Electric fields are used a lot more than Coulomb's law. And electric fields are, in some region of space, there's a field set up by an array of charges. And if you take some other charge, usually called a test charge, and you put it within that field, it will experience a force because of that field. So we'll do some problems with that. And again, it's an analogy with gravity, because if you have a gravitational field and you put a mass in a gravitational field, it'll experience a force due to gravity. And it's the same thing with an electric field. If you take a charge and you put it in an electric field, it'll feel a force due to the electric field acting on the charge. Then from there, we went on to potential, potential energy, electrical potential energy, and then potential. And then we looked at some electronics, electronic devices of resistor, capacitor, and we did do the inductor too, but that's with the magnetism. And so I'll try to cover that today. Okay, let's see if there's anything in the chat here. I'm just going to look over every once in a while. All right, and this happens every so often where I lose. Oh boy. There we go. Okay, so let's start off with the very first question there, and I might even just do a variation on that on this question. So this is a question on Coulomb's law. It says you have a 5 microcoulomb charge, which is placed 5 centimeters away from a plus 7 microcoulomb charge, and is the force attractive or repulsive, and what is the strength of the force? Okay, so let's start off with attractive or repulsive. So attractive, the electric force can be either attractive or repulsive, unlike gravity, which is always attractive. And whenever you have two opposite charges, that's when it's attractive. In every other case, it's repulsive. So if you have two positive charges, they'll repel. If you have two negative charges, they'll repel. A positive and a negative, they attract. So opposites attract, like charges will repel. Well, here you can see that you have two positive charges, so it's pretty obvious that this force is going to be repulsive. Okay. And what's the strength of the force? Well, let me switch to another screen and I'll do this. But if you don't mind, I'm going to use some different numbers because you could just look at the numbers I have. I'm just going to switch them around. If you do want me to actually use these particular numbers, we can do that. But let me just switch it around, do a slightly different problem because otherwise it's kind of boring to do the same thing. And the solution is online. Okay, so I've just switched here to my my whiteboard, and Coulomb's law is this, Q1 Q2 divided by R squared, like that. Okay, and this constant capital K is Coulomb's constant, and let me quickly look it up because I don't use it very often. Coulomb's constant, it's 9 times 10 to the something, but I don't remember exactly. 8.99 times 10 to the 9. Is that right? Just looking off of the yeah, that is. Here it is off of Wikipedia. Let me just cut and paste it into my whiteboard here. All right, and that's to the exponent 9, like that. And the units are going to be Newton meters squared per coulomb squared, like that. Okay, so I've got a lot of digits there. This is way more than we need, so we can actually just round that off to that number there. All right, so there we go. And might as well save this so that I have it for later. Okay, so you know what? Instead of those numbers, how about we pick one charge, which is, I don't know, negative 3 micro coulombs, and another charge, which is plus 5 micro coulombs. And how far apart should we put them? How about we put them 10 centimeters apart, like that? Okay, so just to pick some different numbers. The method's identical to the other one. And how would you do this? Well, it's as simple as just plugging everything in. Okay, so let me bring up my calculator, and let me show you how that substitution is done. So the trick with all of these, of course, is to make sure that you're in MKS. So over here, for Coulomb's constant, so I'm just going to substitute for K here. For Coulomb's constant, it's this number right there. All right. For Q1, we don't have to worry about the negative and the positive. The negative and the positive, all that really gives you is the fact that this force is attractive, right? Because they're opposite charges. So not very deep. Okay, so you don't really, you don't need it. You don't need to substitute those signs into the equation. You just use the signs to determine that the fact that you have a negative charge and a positive charge means that they're opposite charges, so you have an attractive force. Okay, so over here, when I go to substitute this in, I'm just going to put in 3 micro coulombs and then 5 micro coulombs, like this, and then divided by, and what did I say, 10 centimeters, like this. Okay, but squared, like that. Okay, well, actually, let me put in the units so you can see what's going on here. The only I don't know if it's the only mistake, but one mistake you can make is not getting the units right. So we need to make sure that the units are right here. The MKS units, newtons, meters, and coulombs. Well, over here, here's the coulombs, but you have micro. And so you need to know those metric prefixes. Micro is a millionth, or 10 to the minus 6. Okay, and so we got a micro there as well. And then centimeter, centi, is a hundredth, or 10 to the minus 2. And so what we need to do is we need to make sure that we get rid of those metric prefixes. And over here it's 10 times 10 to the exponent negative 6. And over here it's going to be times 10 to the exponent negative 6, like that. Okay, and over here this is a hundredth, so you could go times 10 to the exponent negative 2. Alternatively, you could just move the decimal over to and it'd be 0.1 meter, okay? Whichever you like, all right? And at this point, you're ready to just substitute everything into your calculator, because, that coulomb there will actually, let me just show it to you on the next line. Let me show you how all the units will work out. You see you've got a coulomb there, and then you got another coulomb there, and what will happen is those coulombs will cancel, okay? So that will cancel that one and that one, all right? And then on top you've got a meter squared, but on the bottom you have a meter, but it's squared, and so that will cancel out against that. And you're just left with newtons, and that's exactly what you expect for your force. Okay, and so let me go ahead and plug all of that into my calculator. 8.99 times 10 to the exponent 9 multiplied by 3 times 10 to the negative 6 times 5 times 10 to the negative 6 divided by 0.1. Better do that in brackets. 0.1. And I'm getting this number here rounded off, 13.5 newtons. Okay, so again, these are pretty straightforward problems, and the critical thing being make sure that you're working in MKS units. Okay, and again, this force is attractive, so they'll actually attract one another. All right. Just a comment about the sizes of things. I mentioned this in the lecture, but it's worth mentioning here again. Micro coulomb is kind of a typical size for a charge that you would have in the lab. Let's think about this. These are two charges, and they're 10 centimeters apart. And 10 centimeters is it's a good amount of distance, and yet you're getting 13 newtons of force between them. So a microcoulomb is still pretty big. A coulomb of charge is huge. Okay, to get like a coulomb of static electricity, you need something like a lightning bolt or something like that. So, so there we go. Okay, let me quickly look in the chat, see if there's any questions. Are you going to post this lecture afterwards? So I've got one question. Am I going to post this afterwards? Well, I can post the review, like the actual whiteboard. Okay, so yeah, I'll put the whiteboard up online. Okay, and I'll just say review session, and also the video itself, the live stream, will be online. Okay, all my live streams, they're online. They're like pre-recorded lectures, but the thing is that I get to look at the chat, where I can't look at a chat during a pre-recorded lecture. I can look at the chat here. And do I know how many questions will be on the final? No, it'll be a little bit longer than previous ones, because it's worth 40% rather than 30% of your grade. But I have not written the final yet, so I really can't answer the question how many questions are on there. What I can say is what I usually say is that the final exam will be timed at about 2 hours long. In other words, there's no reason why you shouldn't be able to finish it in in 2 hours. But I'll give you 3.5 hours to actually do it, just to give you some extra time, given the different environment. All right. So there we go. There's one question, and I don't know if I want to put a number here, but I'll just say number 1. This is an example of Coulomb's law. Okay, and well, there we go. Okay, so if there are no more questions about Coulomb's law, let's move on to electric fields. All right, and let me quickly look at the one that I have online. And I'll do a variation on that one. Okay, so let's see here. What do we have online? Oh yeah, the one I have online is kind of an example that I do a lot, and that is an example where you have an electric field actually suspending a droplet because gravity wants to pull the drop of water down, whereas an electric field wants to pull it up, and the two balance with one another. And this is actually inspired by an experiment that was used to discover the electron. It was the Millikan's oil drop experiment. But you know what? Rather than do this problem, let's just do a more generic electric field problem, and maybe a couple of electric field problems. And I think that would be a little bit more. It'll focus more on electric field than this particular problem does. Okay, so let me switch back to my whiteboard here, and let's do an electric field problem. Um, Let me think of something. Let's do something kind of simple here. Um, like your wall socket. Your wall socket, it's about 120 volts, and the distance between the two prongs is about 1 centimeter. That turns out to be about a thousand newtons per coulomb electric field in that area. Okay, so 1,000 newtons per coulomb, and you hear the number 1,000, it sounds like a lot, but it's not really that much. So let's just see what kind of force there is on. I don't know, let's say a proton, because we always play with electrons. But let's say what the electric field is on a proton that's in 1,000 Newton per coulomb field. So we place a proton in an electric field with strength E is equal to 1,000 newtons per coulomb, like that. Okay, and I can ask a couple of questions. A, what is the force on the proton? And B, what is the acceleration of the proton? Okay, in that field. All right, so easy enough, I think. Okay, and so the first question is, what is the force on the proton? Now, what do I give you? I give you the electric field, okay, and force. And so there's a relationship between force and electric field. And what is it? It's this equation here. The force is equal to Q times E, like that. Okay, so this equation is actually the electrical equivalent of, let me just say that here, electrical equivalent of F is equal to mg, like that. Okay, let me space it out a bit. There you go. All right, so why? Well, because you see, if you put a mass in a gravitational field, then you're going to get a force on it, mg. But if you put a charge into an electrical field, you're going to get a force QE on it. Okay, and so there you go. Now, so I'm asking for the force. Great. So you want to calculate the left-hand side here. And you need the charge, and the charge of a proton. You go, oh no, what's the charge of a proton? Well, I would give it to you. Okay, it's actually the same as the charge of an electron, except that the electron has a negative charge and the proton has a positive charge. Okay, and so you could just look that up. I'm going to do that right now so that I can get all the some more digits. I kind of remember the number, but charge of a proton, there we go, came right up. And so here it is. It's a big number. Well, not a big number. It's got a lot of digits. I mean, it's a small number. Okay. So there is the charge of one proton. Okay, in coulombs. All right. And what's the electric field? So there's the Q. And what's the electric field? Well, the electric field I gave you was 1,000 newtons per coulomb. I'll put the units in there so you could see how they work out. And you'll notice that the coulomb here will cancel the coulomb there. Okay, I can actually, I don't know, I hope this isn't too trivial, but there you go. This is showing that the coulombs will cancel. And what's left over are the newtons. Okay, and this is just going to give that F is equal to, let me just round this off like that, times 10 to the, not negative 19, but you're going to add 3, right? So it's going to be 1, 2, 3 there. So it's going to be times 10 to the negative 16 newtons. Okay, so there you go. There is the force on the proton. All right. Now, part B says, what's the acceleration? Now, here it's not so much a question of electricity, but I do want you to understand that, this is just a plain old force. And what's the relationship between force and acceleration? Well, it's Newton's second law, F equals ma, like that. Okay. So Newton's second law, like that. Well, I want A, so all I have to do is take the force and divide it by the mass of the proton. And, I wouldn't expect you to, remember these numbers. So the force, we just calculated that. There it is. All right. And the mass of the proton, let me look that one up. Again, I kind of remember these numbers, but I don't want to type something incorrect in the chat here. And the mass of a proton is, I'll give you a whole bunch of digits here. I'm just cutting and pasting directly out of Wikipedia. Okay, there it is. And let's get rid of these last few digits. This bracket in there just means that that's an uncertainty. So let's just get rid of that there, like that. Okay, and I'll put a little caret in there. So it's like 1.67 blah 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 times 10 to the minus 27 kilograms. Okay, and let me do that on my calculator. 1.6 times 10 to the exponent negative 6 divided by 1.67 times 10 to the exponent minus 27. And gives me a huge number, which is what you would expect actually. Copy. I'll give you all the digits here, but this is a crazy number of digits. Okay, so there it is. And this is going to be in what? Well, this is newtons. This is kilograms, so this is going to be meters per second squared, like that. Okay, and too many digits, so let's count how many digits there are. There's 1, 2, 3. I'll put some commas in there just to show you the division. Another 3, and there's another 3. So it's going to be 95.8 times 10 to the exponent 1, 2, 3, 4, 5, 6, 7, 8, 9 to the exponent 9 meters per second squared. Or we can even reduce that, make it a little bit nicer, 9.58 times 10 to the exponent 8. Sorry, no, 10, like that. Okay, meters per second squared. Okay, so here, let me just put each one on their own line. All right, so at this point, you can look at this and you could say, wow, that's a huge acceleration. That's right, it is. It's absolutely astronomical acceleration. But that's to be expected because, proton is a very light particle. And so, even if you have a small electric field of 1,000 newtons per coulomb, it's going to cause a tremendous amount of acceleration. Okay, let me look in the chat to see if there's any questions or any requests. And no, nothing new. Okay, I'm not seeing any new questions. Again, there might be a lag, so if you typed a question and I don't see it, I'll catch it after I do the next one. Okay. Now I do want to do another electric field problem, but they're pretty easy at this level. So actually, let me introduce potential next. And what I'll do is I'll tie potential to electric field, and then we can do some electric field problems in the context of potential. Okay, so just to remind you that what potential is, there's potential and potential energy. Okay, and they're different from one another, so they cause confusion because the name is similar. Potential is volts, and potential energy, well, that's just energy, that's joules, like this. Okay, and the relationship between potential and potential energy, like if you've got something like a battery, and the battery is like a 9-volt battery, what does that even mean? Okay, it means the battery has a potential of 9 volts. What does that even mean? It means that the battery will deliver uh, 9 joules of energy for every 1 coulomb of charge that it pushes out. Okay, so potential is basically potential energy per, and this is the part that it's a little bit different, per coulomb charge, or per unit charge. Okay, so it's not just how much energy there is, but how much energy you get for every coulomb that gets delivered. Okay, and so potential, unfortunately, potential, both the symbol for potential and the units for potential are V. So V as the symbol is going to equal your potential energy, like this, divided by your, you know what, I think I used U in the lecture, so let me use that, divided by the charge. Okay, or the other way that formula could be written is that the potential energy is equal to QV. Okay, now you can compare that formula, F equals QE. Okay, so you can just compare those two formulas like that. Okay, and so this basically relates potential energy and potential, and this relates force and electric field. So the electric field is the force per unit charge, and the potential is the potential energy per unit charge. Okay, so okay, just a little bit of an introduction to the next question. Let's take a quick look at what I had online for this question, and maybe I'll do a variation on that. Okay, so let's see here. What do I have? I have okay. So this is a classic problem for potential. Two parallel plates are attached to a 100-volt battery, and a droplet of, oh, this is with a droplet of water. Okay, so let me do a variation on this one. Okay, so yeah, here we have a droplet of water with some charge on it being accelerated between the two plates. So I'll do a little variation on this. Okay, so all right, so let's see, what should we do? Let's put a proton between, we'll kind of carry along on the previous example. So we place a proton in uh, between two parallel plates and apply a 10,000 volt potential. Okay, well, yeah, okay, we place a proton between two parallel plates. How about we place a proton in the middle of two parallel plates and apply a 10,000 volt potential. Okay, and let's ask some questions. Okay, so question number one, two parallel plates and 10 centimeters apart. Okay, and apply 10,000 volt potential. All right, now we can ask some questions. All right, here's question number one. What is the electric field between the two plates? Okay, so this is going to relate electric field. Oh, I'm sorry, guys. I forgot to switch to the... okay. Sorry about that. Let me see if there's a... Yeah. Okay, Aaron, I saw that. Yeah, thanks. Flip to the notepad. I did. Okay. Yeah. Here it is. So here's the. Let me just start again with number three. So we got a potential V and a potential energy, which is potential is measured in volts, and potential energy is measured in joules. Okay. So if you have like a 9-volt battery, what does that mean? That means that the 9-volt battery delivers 9 joules of energy for every 1 coulomb of charge that flows out of it. And the relationship is that potential is equal to the potential energy per coulomb of charge. Okay, and so written in symbols, that's V is equal to U. So U is the symbol for potential energy that I'm using here. Sometimes I'll write PE, sometimes I'll write U. So it's the potential energy per unit charge, or U is equal to QV. So potential energy is Q times the potential. And you can compare that to F is equal to QE. Okay, and so there you go. Okay, so that's the formula we're going to use here. And here's the question. We place a proton in the middle of two parallel plates 10 centimeters apart and apply a 10,000 volt potential to the plates. Okay, and what's the electric field between the two plates? In fact, let me say not just to place it in the middle, let's place a proton exactly in the middle, and we apply a 10,000 volt potential to the plates. Okay, just to be precise. All right, so great. Okay, let me see here. Yeah, I apologize for just not paying attention to having not flipped back. Okay, so the first thing is you look at this and you go, is there a relationship between potential and electric field? And the answer is yes. Okay, the electric field is actually the rate at which the potential changes over distance. Okay, and so I don't want to rederive that here, but you could write basically that the potential is equal to E times D, like that. Okay, so this basically says that the potential increases as you move from one as you move into the field. Let's just say it that way, as you move into the field. Okay, so let me try to explain. Let me try to explain this intuitively. Okay, so what's going on with that? All right. Well, imagine. Let's take gravity as an example. Okay, so imagine you're at ground level and you have a ball at ground level. All right. Well, if the ball at ground level has no potential energy associated with it, as you lift the ball, what you're doing is you're doing work against the gravitational field. You're doing work against the gravitational force, which is down, and that stores potential energy into this ball. And then when you release it, it falls back down. The electrical equivalent of that is if you've got a charged particle and you pull it into the field against the direction that it wants to fall. So you pull it into the field. The further you pull it into the field, the more potential you get in it. Okay, so here's the field. All right, and you're going to pull that charged particle into the field. The further you pull it into the field, the more potential you've given it. Okay, and so that's where this comes about. All right, and I gave a deeper discussion of that when I did the lecture. So here I give you the potential. It's 10,000 volts over a distance of 10 centimeters, and I ask you for the electric field. And so it's as simple as this. Just rearrange this equation, V divided by D, like that, and that's going to be, well, 10,000 volts over a distance of 10 centimeters, like that. All right. Oh, okay, and we want this in MKS, so we want to get rid of the centimeters there and convert it to meters. And so this is going to equal, in meters, that's going to be 0.1 meters, like that. And so you're going to get, let me put these on different lines so it's a little easier to read. All right, you're going to get 100,000 volts as your answer. All right, volts per meter, sorry. So there's your electric field, volts per meter. All right, that answers part A. Now at this point you might say, wait a sec, up here when we were working with electric field, you said the electric field's units were newtons per coulomb, but down here you said that the electric field units are volts per meter. Guess what? A volt per meter is the exact same as a newton per coulomb. Okay, I don't want to prove it here, but they are the same units. All right, so there we go. All right, let's see if there's any questions with that. All right, no questions there. Let's continue now. Now, I obsessed a little bit about where we're going to place the proton. We're going to place the proton exactly in the middle of the two parallel plates. Okay, so a little hard to draw plates, but let me just try to draw them like this. Okay. So there are the two plates. These dashed lines are supposed to indicate the wire that's attached to them. And we could say maybe this is the positive end here. Okay, and this is the negative end over here. Okay, and the two plates are 10 centimeters apart. And I put the proton right in the middle. Okay, now where does the proton want to go? The proton, which is that asterisk, wants to, let's put it in brackets, fall. I'm trying to make that analogy to gravity. Fall to the negative plate. Okay, right? Because it's repelled. You know what? Let me change that. How about this? This is maybe a little better symbol for the proton. If I can type correctly. There we go. All right. There we go. The proton, which I'm trying to indicate, is that positive guy right there. Okay, it wants to fall away. It gets pushed away from the positive plate and towards the negative plate, and so it wants to fall towards the negative plate. But how far is it falling? It wants to travel a distance d equals 5 centimeters to the negative plate. Okay. Now, a little hard to draw here, but at this point, you've got 10,000 volts. Okay. And at this plate, you're going to have 0 volts. So what do you think you have right in the middle here? Well, if you think about this formula, or better yet, this formula, as the distance increases, the potential increases along with it, okay? And so right in the middle, you're going to have a voltage of 5,000 volts like that, okay? So the proton is actually at a potential of 5,000 volts. Think about it this way. If the proton were at the negative plate, where would it want to go? It's where it wants to be. So it's at 0. If the proton were at the 10,000 volt, that's as far away as possible. So it's at the full 10,000 volts. If it's halfway between the two plates, then it's at 5,000 volts. Okay. And so part B, I didn't ask a question yet, but what is the potential midway between the two plates? And the answer is 5,000 volts. And if you want to see that coming out of a formula, okay, you could say V is equal to E times D, and E is the 100,000 volts per meter. But now we're not the full 10 centimeters away, we're only 5 centimeters, okay? And so that's going to equal this times 0.05 meters. And when you multiply those numbers out, you're just going to get 5,000 volts. Okay, so I hope that makes sense. The electric field is kind of like, how much voltage do you get for every centimeter that you walk into the field? Okay, or actually, I guess in MKS, for how much voltage do you get for every meter that you walk into the field? So this basically says that for every meter that you walk into this field, you gain 100,000 volts. Well, if you've walked into the field only 5 centimeters, then you've gained 5,000 volts walking in that in 5 centimeters. Okay. I hope that makes sense. Otherwise, just ask questions in the chat. Okay. And well, that answers part B. Okay. That answers part B. Okay. So now part C here is going to be, well, we did one with the acceleration. That was number 2. Well, what's the force on what's the acceleration? Let's just say, what's the potential energy? What is the potential energy of the proton? Okay, midway between the 2 points, obviously. Okay, and for that one, we're going to go back and we're going to use this formula right here that relates potential energy and potential. Okay, like that. Okay, and the charge of the proton, well, you have that from above. Let me do this each step on a different line here. The potential, the charge of the proton is right here. Okay, there was the charge of the proton. All right, scroll back down here. Let's get rid of some of these decimals. Okay, there you go. There's the charge of a proton. Incidentally, it's also the charge of an electron, except the sign is different. And where's the proton? The proton is at 5,000 volts. Okay, like that. And just multiply those numbers together. Let me bring up my calculator to do that. So I've got 5,000 multiplied by 1.6 times 10 to the exponent negative 19 will give me, oh, how come I got 0? I don't know. And we'll do it this way. It's 8,000 times 10 to the minus 19. Okay, and you know what, just to show you that the unit would work out, what's a volt? A volt is a joule per coulomb, right? So you can see the coulombs will cancel, and so your answer will come out in joules like that. And let me just move the decimal over to make this look nice. 8.0 times 10 to the, so we're moving it over 3. 1, 2, 3. So that goes from negative 19 to negative 16, like that, joules. All right. And let me see if there's any questions in the chat. Nope, looks good. So if If I don't see any questions, I assume you guys are okay. There we go. Okay, so there's part C. Part D is, well, here's the proton that's in the middle there. And we might hold it there for a second, but we're going to let go. And when we let go, what's it going to do? It's going to quote unquote fall, okay, to the negative plate there. Okay, and I say quote unquote fall because it's not gravity that's doing it, it's electricity that's doing it. Okay, it's going to fly over to the negative plate, and I can ask the question: how fast will the proton slam into the negative plate? Okay, because it's going to be moving quite fast. Now, here it is. This is all potential energy. So this is just like, gravitationally, when you lift something, you've got gravitational potential energy. But here, it's electrical potential energy. And that electrical potential energy is all going to become kinetic energy. So all the electrical potential energy becomes kinetic energy. Okay? And so that basically says that U is going to equal 1/2 mv squared, like that. And we have the energy. There it is, the total energy. That's got to equal 1/2, okay, times the mass of the proton. And I gave you that above. Let's go get that. That's at 1.67 times 10 to the minus 27. There it is. Okay, so let's grab that number from there and put it in there. And get rid of some of these decimals because that's too much information. Okay, and times v squared. Okay, so there we go. We've plugged it all in. Now what do we want to do? Well, we want to rearrange this equation. Okay, so basically we have, this number. Everything's in MKS, so I'll just drop the units. Okay, so we have that number divided by all of this. Okay, if you're doing it on your calculator, it's always safest to put brackets around everything. And let's get rid of that. All right, so this the way I've arranged it here, it's ready to go in your calculator, and that'll give you v squared first, and then we'll take the square root after that. Okay, so let me do that in the calculator, and let's see, what do I get here? 8 times 10 to the exponent negative 16 multiplied by 2 divided by 1.67. Oh, better put brackets there. Times 10 to the negative 27. And I get this huge number here like that. I'll just write it down, okay? But we now want to take the square root of that number. And so what's the square root of that number? The square root of that number is still a big number, but, there it is, okay? And everything was in MKS, so it's meters per second. And too many digits there, so let's round it off properly. So what would we say here? It's like 1, 2, 3, 4, 5. So it's like 9.79 times 10 to the, what did I just say? 1, 2, 3, 4, 5 times 10 to the 5. Meters per second. That's not a 2 there. That is supposed to be seconds, like that. Okay. All right. So very fast. Okay, but not too fast, because the fastest speed would be the speed of light, which is 3 times 10 to the 8 meters per second. Okay, so it is, it's significantly slower than the speed of light, but it's still very fast compared to ordinary speeds. Okay, so this is pretty much a complete example that shows potential here and its relationship to electric field. So this is the first question, was the relationship between potential and electric field, and that is the formula, but you really have to understand this formula as kind of being a gradation as you go from one plate to the other. And so, yeah, there's a constant electric field between these two plates, but that constant electric field grows as D grows. Okay, that's what this D, think of the D as kind of like a variable that'll vary over the distance. So if you're at 0 distance into the field, well, then you're at 0 volts. But as you walk further into the field, D gets bigger and bigger and bigger. E is constant, but as D gets bigger and bigger and bigger, V gets bigger and bigger and bigger. So here I am walking into the field. As I walk into the field, I get bigger and bigger and bigger. Halfway, I'm at 5,000, and the full way, I'm at 10,000. Okay? And so that's the first part. The second part was making use of the relationship between the potential and potential energy. And the potential energy is just a charge times the potential, because after all, what is potential? It's energy per unit charge, okay? And then once you've got the potential energy, I mean, you can do things with that potential energy, like you can make it converted into kinetic energy, and when that potential energy converts into kinetic energy, then you've got a certain velocity, and there's the velocity that this proton would slam into the negative plate. Okay, I think I did the electron in my the lectures, but you know, you can do any charged particle, and in the examples that I have online, I actually did a charged droplet. Okay, let me see if there's any questions in the chat here. No, I'm not seeing any questions. I mean, I assume you guys are okay. If that's the case, then we're kind of done with this. Let's take a look at what I have. What else I have here as questions. Okay, so that was like question number 3. Okay, well, question number 4 and the rest, they're starting to head into the capacitors. Okay, now I didn't have all my capacitor questions here because I realized that I missed a few kinds of capacitor questions. There's just plain old capacitor questions, like, and then questions on the definition of capacitance, questions on capacitors in series and parallel, and then also questions about putting together capacitors or building capacitors out of parallel plates. And so that's why if you go back a level here, you'll see that I have you know, some questions here. Okay, and then there's solutions, and then I've got those extra questions there, and those extra questions have some questions about capacitors in them as well. Okay, and so what I'll do is I'll try not to jump around too much, but I'll do all the kinds of questions that we can do with capacitors together for our review. Okay, so let me not forget to switch back to my whiteboard here. Here we go, back to the whiteboard, and let's start doing some capacitor questions. So the first one, let me see what number I'm up to here. I'm up to question 4. So the first kinds of questions that you might get with capacitors, just plain old definition of capacitance. Okay, and so here's a very simple, trivial, but nonetheless important to understand, you know, the definition of capacitance. Okay, and let's just say we have we apply I don't know 15 volts to a 35. Now the units of capacitance are farads. Farads are very big, and so typically you're down into the microfarads and nanofarads. You can even get down as low as picofarads. Okay, and so let's do a nanofarad capacitor. All right, just to give you another unit there. Okay, we apply 15 volts to a 35 nanofarad capacitor. How much charge is accumulated? Okay, so this is just purely the definition of capacitance. And what is the definition of capacitance? Well, it's how much charge is accumulated on the plate per volt applied. Okay, so capacitors are usually made out of parallel plates like this. All right, and what will happen is if you apply a positive voltage here and you apply a negative voltage there, you're going to get a charge accumulated on the plate. But the way that charge will work is, let me see if I can do it up here. The way that charge will work is you'll get plus Q on this side, and on the other side you will get negative Q. Okay, this Q in here, it's actually not the sum of these two, because that makes no sense. If you were to add up the total charge on the capacitor on both plates, they cancel, because one is positive and the other is negative. So this Q here is just the absolute value of the charge that's accumulated on any one of the two plates. Okay, because one plate will accumulate a positive charge, the other one will accumulate a negative charge. Okay, and it's given the symbol capital Q rather than a small case q, because you can see up here you go, well, why were you using little q for everything? Okay, and then down here I switch to capital Q? Because this capital Q is more than one little q. There's like lots of electrons that'll add up to this accumulated charge here. So that's why we usually say the word accumulated, because it's more than just one little electron or lack of an electron. Okay, so that's it. There's the definition, and we're going to use that definition to answer the question. I'm asking how much charge is accumulated, so I'm asking you to calculate Q, and so Q is going to equal C times V, like that, and C is 35 nanofarads. Okay, and V is 15 volts, like that. And there you go. Now, you could actually leave this in nanofarads, okay, right now. And if you did that, then you would get your answer in nanocoulombs. Let me do that first. Okay, and so it's 35 times 15. But I'll show you what nano are in just a second. So that turns out to be 525. And whenever the units here, a coulomb is a farad times a volt, like that. Okay, and so this will be nanocoulombs. All right, and I'll explain the nano in just a second. Let me explain the farads and the coulombs here. Okay, so first, let's not confuse things. Unfortunately, there are too many symbols here, and so this C here means capacitance in this equation. Okay, so as a symbol, C means capacitance, but as a unit, C means coulombs. Okay, so a coulomb is a farad times a volt, or another way to think about this is that a farad is a coulomb per volt. Okay, that means if you had a 1 farad capacitor and I apply 1 volt to it, I would accumulate 1 coulomb of charge. So a farad is huge. First of all, a volt is tiny. All right, I mean, like even those little batteries we have are like 1.5 volt batteries or 9 volt batteries. Okay, and that's puny. You know, our walls have 120 volts, and some wall sockets have 220 for like bigger appliances. So a volt is pretty small. A coulomb is huge. So if you got a big number divided by a small number, you're going to get an even bigger number. So a farad is big. So generally speaking, capacitors are down into the micro, nano, or picofarad range. Okay, and just for your notes here, micro, okay, which I can't draw very easily. It's that symbol mu. Okay, micro is 10 to the negative 6. Okay, it's millionth. Okay, and nano, which is what I have here, is 10 to the exponent negative 9. Okay, and pico, which you probably haven't seen. You saw it in just one tiny little lecture where I did the LC circuit. There you're going to have 10 to the minus 12. Okay, and so this number here, Q, is equal to this. You could leave it like that, or maybe on a multiple choice test I might have the answer like that. But that nano there, that nano is really times 10 to the minus 9 coulombs. Okay. So I hope that makes sense. I mean, the problem, the math is pretty easy here, but it's just this business of getting the metric prefix right, because capacitors, like a farad, is very, very big, and so lab-sized capacitors are going to be into the nanofarad range. All right, let me see if there's any questions in the chat. Nope, no questions. How many people are watching? 9 people are watching. Good. Okay, so all right, well, that's one question with a capacitor. Here's another one. Now this one isn't part of the first series of problems, it's part of the second series of problems, and it's like, how do you build a capacitor? And the answer is you could do it with parallel plates. So let me see if I can just steal that diagram right there. Here we go. So here are my parallel plates. Okay, like that. And the other thing is that you can build a capacitor by just 2 parallel plates, but to make a good capacitor, you want to enhance the capacitance, and you can do that by putting this material in the middle called a dielectric. Okay, and so I hope you can understand that diagram. These guys here, so let me maybe explain what my diagram means. The parallel there is a parallel plate. The X is a dielectric, and it's just some material which enhances capacitance. Okay, it's just like, what could it be? It could be ceramic, glass, and it has to be a non-conductor. So let me just say that too, a non-conducting material. You can't use steel. Steel would, if you put steel between two capacitors, you've just built a wire, because the electricity will just go from one side to the other. There's no way you'd be able to keep the charge from like here you have the positive charge on one side and the negative charge on the other way side. If you put a wire between these two, I mean, the negative will just flow right to the positive, and it'll short out the capacitor right away. So this material in here has to be non-conducting. Okay. And if we're going to build a parallel plate capacitor, you're going to have these two plates. You're going to put some dielectric in between, and the geometry of the plates will actually determine what capacitance you get. Okay, so in this question, we build a capacitor out of two parallel metal plates. Okay, so like there's a lot of ways to make a capacitor. They don't have to be parallel, all those things, but that just makes for the much more complicated formula. This is good enough to get an idea of how capacitance arises out of some kind of geometry of plates. Okay, so we got these two parallel plates. Each plate it has dimensions. Oh, I don't know. Let's make them big. Um, 45 centimeters by, I don't know, 35 centimeters. Okay, so that's the area of the plate. The two plates are kept, let's say 1 centimeter apart by a dielectric material, by a material with dielectric constant K equals, I don't know, this doesn't matter. Let's say 11.5. Okay, there are no dimensions to the dielectric constant K. Okay, and so there you go. How does this work? Well, the capacitance is going to equal, you know what, guys, I'm going to bring up a word processor. I really want to show you these symbols, but I just can't. I have to cut and paste them from another. I can't directly type them in here. I actually have to cut and paste them. So I might as well do this, and just give me a little second here. So it's going to be the dielectric. I'm going to replace this in a minute. It's epsilon naught, which is the dielectric constant of free space, multiplied by the area of the plates divided by d. Okay, and where's my thing? Okay, so let me get a couple of characters here. Okay, there's one. All right, and over here, micro, the proper symbol is, there it is. There's the proper symbol for micro. Okay, so great. Now I can properly do micro. And the proper symbol for epsilon naught is epsilon copy. Okay. And there we go. It's got a little knot at the end there. Okay, great. That looks a lot better. Okay, so sorry for that little bit of a delay, but I really wanted you to see this properly. Okay, so what is this saying? This saying, look, if you got two parallel plates and they have some area A, okay, that's not the area of the two plates. It's the area of any one of the two plates. Okay, they have an area A. Each plate has an area A, and you put them at a distance d apart. They immediately have a capacitance. And if you want to enhance that capacitance, say by a factor of 11.5, then you put some dielectric in the middle. This constant here, this is just a property of empty space, and it's called the permittivity of free space. It's the ability of free space to simply sustain electric fields. Okay, and this sounds a little strange to students, but free space, that is empty space, it's not without properties. It has properties, but the properties of free space are, um, the ability to sustain an electric field, the ability to sustain a magnetic field, and so on. Okay, one more thing about this equation, then I'll solve it. And you go, well, look, you guys are not even going to be physics majors. You go, why should I care about this? A lot of the stuff we're studying it in the abstract, but it applies to biological systems. For instance, cell membranes. Okay, cell membranes, have an area. Like there's a top and a bottom to the cell membrane. They have an area. They're a certain distance apart, and there's some lipid materials in the middle with a dielectric. And so cell membranes, they actually have a capacitance. Okay, cell tissue has a capacitance associated with it, and these kinds of properties are not trivial when it comes to certain types of therapies that are done, where you might use like electrical stimulus on the muscles. Okay, and when you do that, you're going to wonder about things like what's the capacitance of this tissue, what's the resistance of this tissue, and so on. So that's what the connection is between this abstract stuff and biology. And so I wanted to teach you this because this is going to give you an idea of how capacitance arises between two parallel plates. Well, rather than two parallel metal plates, how about two parallel plates of a cell membrane? Okay, and so, okay, enough of that. Let's just plug in the numbers. Well, first, the area. I don't give you the area directly. There it is there, and I say for each plate. And of course, we got to convert to MKS units. That's going to be 0.45 meters multiplied by 0.35 meters, and that gives me, do this on my calculator, 0.45 times 0.35 is equal to meters squared. Okay, there you go. There's the area. And now the rest of this is just plugging in. So for K, we have 11.5. It's dimensionless. It's just like an enhancement factor. It just means like without it, you're going to get some capacitance. With it, you're going to get a capacitance which is 11.5 times bigger. And yeah, the enhancement due to dielectrics can be very big. Okay, and this epsilon naught, what is that? Well, you got to look it up. Permittivity of free space. And just looking at the Wikipedia page, they call it the vacuum permittivity, which is exactly the same thing. Permittivity of free space, vacuum permittivity, they mean the same thing. Okay, and that's in farads per meter, like that. Okay, let me get rid of a lot of these decimals because that's an insane number of decimals. Okay, and so what's this? This number here is actually that epsilon naught. The area, we just calculated that. It's this number right here. And the distance between the two plates, I said, is 1 centimeter, but we have to do that in MKS, so that's going to be 0.01 meters, like that. Okay, I'll give you that number in a second, but take a look here. The units work out, don't they? Because you see that meter there? And that's on the bottom. That's in the denominator, and there's another meter in the denominator there, like that. And there's 2 meters in the numerator, and so they cancel, and all that's left is the farad. Okay. And so what's this number going to equal? Well, no, let me do it on my calculator here. So 11.5 multiplied by 8.85 times 10 to the exponent negative 12 multiplied by 0.1575 divided by 0.01 equals, oh, I wish it hadn't done that. It rounded off on me in a terrible way. Well, all right. There's probably more decimals there. I'll fix that in just a second. Let me see. I hate these calculators. All right, so let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 2 times 10 to the exponent negative 10 farads. There's more decimals here. Let me just get those extra decimals there. I don't know. This calculator just sometimes it'll just like round off for no particular reason, and I don't know why. 0.15. Oh, geez, it's 1.6. So it's actually 1.6 like that. Okay, so if someone does it in the chat and sees that if did it wrong, just let me know. But I think I got that right. Okay, so let's see, 11, 8.5. Yeah, I think so. And it just rounded off the 1.6, it rounded it off to the 2. Okay, so there you go. Now, if we actually wanted to write this as in terms of metric prefixes, that's kind of useful to do. Oh, sorry. That's going to be, can write this as 0.16 times 10 to the exponent negative 9 farads. Okay, and why did I write it that way? Well, because what's 10 to the minus 9? Okay, 10 to the minus 9 is nanofarads. All right, let me see any questions in the chat here. No, I'm not getting any questions in the chat. Of course, there's a bit of a delay, so I'll wait just a second. All right. Still any questions? No, no questions. Okay. And let's go on and do another problem here. So where have I gotten to? I've gotten to definition, parallel plates. Okay, you know what the next thing is? What happens when you have capacitors in series and parallel? So this is capacitors in series and parallel. All right. Okay, so why is this useful? Maybe I should mention that. Again, if you're looking at biological tissue, you might have many layers of tissue, and between all these different layers of tissue, you have like one capacitance with one layer, another capacitance in another layer, another capacitance in another layer. And you might ask the question, how are these tissues related to one another? Does the electricity have to pass through them in series? Does it have to pass through them in parallel? And that's why this is important, because there's going to be an effective potential, or I guess I call it an equivalent potential, depending on whether the capacitors are in series or parallel. Okay, so there's a couple of problems for this, and let's do the easier one first. So we have a, I don't know, 16, and let me grab my little micro from up here. We have a 16 microfarad capacitor in series. What does series mean? It means that one capacitor is right beside another capacitor, and the current has to travel through both of the capacitors. Okay, so that's almost the definition of series. The current has no choice. It has to pass through one, and then it has to pass through the other. Okay, so in series with, I'll put the diagram down here, in series with a, I don't know, a 32 microfarad capacitor. Okay, what is the equivalent capacitance? All right, and so here what you have to remember, and you know what, might as well give you part B to this question right now, because it's going to be the same, but I'm going to change series to parallel. Okay, and parallel is a little harder to draw. Might try to do that afterwards, or maybe I'll just cut and paste from what I have online. But you have to remember the formula for combining them in series and parallel. Okay, so for capacitors, when they're in series, the way I remember it is capacitors, series, reciprocals add. Okay, and so you get 1 over the equivalent capacitance. Okay, Q equivalent is like, you could take these two out and you could totally replace them with just one capacitor, but this capacitor has to have a special value, which is the equivalent of those two capacitors. Okay, so here's the equivalent capacitance, and it's the reciprocal of C1 plus 1 over C2, like that. Okay, and in this case, we have that 1 over 16. Now here you say, well, do I have to convert to MKS? Well, you know what? If you use microcoulombs here or microcoulombs here, then the answer will come out in microcoulombs. You got to be careful, and I'm not to be tricky or anything, but just make sure that they're both the same, because I might have one in micro and the other one in nano, and make sure that you use the same units. But if everything is in microfarads, then of course the units will come out in microfarads. So I have 1 over 16 divided by 1 over 32. So here's that's like C1, and we can even put that in the question. I have C1 equals a 16 capacitor, and I have C2 equal to 32 microfarad capacitor. Okay, and so what's that going to equal? Well, do that on the calculator. So 1 divided by 16 plus 1 divided by 32 is going to be this number here. Okay, but we're not done yet, because that's the, in fact, let me write that in here. That's the reciprocal. Okay. All right, so you got to take the reciprocal. So you take the reciprocal of the original ones and add them together, and then take the reciprocal of that answer, because that's going to give you C equivalent. And the reciprocal of this number is, there we go, like that. Let me just round it off, 7. And what are the units? Well, everything is in microfarads, so there it is. Okay, easy enough. All right, so in series, the reciprocals add. In parallel, they just add. Okay. What does a parallel circuit look like? Oh geez, do I want to? Yeah, let me try to draw it. Let's see here. Okay, so this would be like C1 here, like that. And then down here, I'm splitting the wire here like this. And here's my here's my second capacitor, like that. And I don't know, guys, this is the best I can do with ASCII. Okay, how's that look? Yeah, kind of, sort of. All right, so here we go. We got like here's C1 up here, and here's C2 down here, like that. Okay, so well, it's as simple as just doing C equivalent is equal to C1 plus C2, like that. Okay, and so it's going to be 16 plus 32, which is going to equal 48, and the units are microfarads. All right, so that was pretty trivial. All right, let me see how we're doing in the chat here. All right, still 9 people watching, and no questions in the chat as far as I can see. Okay. All right, so now I'm going to take a break in a minute, but I'm going to do one more question first. So here's question number 7. And for this one, let me actually briefly switch back to that's the second set of questions that I had. So let's go over here. Whoa. And let's go to the our Moodle site here. Okay, so you see how I have the first assignment and then I have those solutions there. Okay, so here are extras. So if you click on the extras here, like that, I did the resistors and capacitors out of order. Not that it matters much, but I really want to do this question together, this question number 3 together. Okay, so let's copy that and paste it into there, like that. Now, I know this is online, and I'll put the solution online. I guess I could just for this one, maybe I'll just change the numbers a little bit so that we have some different numbers to work with. Okay, but I still want to do this particular problem because it's a bit of a challenging problem, and I will have something similar to it on the test. So we want to make sure that we know how to do that. Okay, so let me switch back to my. There we go. All right. So all I did was I copied and pasted it there like this. And what I'm going to do is just for the heck of it, let me just change some of the numbers here. And I don't know, let's make this like instead of 25 volts, how about we make it 100 volts? Okay. And instead of 10 micro, let's get rid of these micros here. Let's do nanofarads. Why not? Okay, and this is nano, and that's nano, like that. And let's just change these numbers to like 30, 45, and 5. Okay, there we go. All right. Not that the numbers make much difference. There is one other way of connecting these that we could also do as well. But I think let's do this one for now. There's all of next week that we can review, and I'll probably return to this circuit and do yet another variation of it, not to overdo it. Okay, and let me see here. I missed the beginning. How many? Oh, yeah. Christine, I'll have to answer that question later. Okay, let me just finish off the lecture, because we're going to be done in about 5 minutes anyhow. So, all right, let's take a look here. Let's see here. What's the total capacitance of the circuit? All right, and total capacitance of the circuit, what you do is you reduce the circuit 2 capacitors at a time, and you have to decide which 2 capacitors to use and whether they're in series or in parallel. And so these 2 here, they're in series. Okay, you could try C1 and C3, but they're not really in parallel because C2 is in the way. And so the first thing you want to do is reduce C1 and C2. And so for the to answer question A, first reduce C1 and C2. They're in parallel. So reciprocals add. Okay. And so we're back to this formula right here. Like that. Okay. Oh, I made a mistake here. Hold on. All right, right here. There we go. Okay, and you know what? I'll just show you the substitution of the numbers and then just calculate it directly, because at this point it's pretty trivial, right? So C1 is 30 nano coulombs, and we're going to work all in nano coulombs. Sorry, nanofarads. Nanofarads. So C1 is 30 nanofarads. C2 is 45. Okay, and if you work that out, you get C equivalent is equal to 1 divided by 30 plus 1 divided by 45, close brackets. I'm getting 18. Okay, that sounds about right. 18 nanofarads. Okay, now at this point, we've reduced the circuit to this. Okay, you see these two? Get rid of them. And this one, you can get rid of that one. Okay, and you've basically reduced it to this. Oh, kind of lopsided a bit. All right, there we go. Okay, and we can actually, instead of calling this C equivalent, we could call it C12 because it's the effective C12, and so this is now C12 like that. Okay. All right, now we're not done yet. We've reduced C1 and C2, so now next reduce C12 and C3. Okay, they're in parallel, aren't they? And that's as easy as the effect of C123 is just C12 plus C3, and that's just going to be 18 plus, what did I say? That one's 5. So this one is 18 nanofarads, and this one was 5 nanofarads, like that. And so if we add the two together, we get 23 nanofarads. And there you go. That's the answer. The equivalent capacitance of the whole circuit is 23 nanofarads. Okay. Let me see what's happening in the chat here. Okay. Technically speaking, this is when our class would have ended. I'm going to take a break because I don't want like I don't want to run into like potentially other people's classes because I know some people are doing these things synchronously, other people are doing them asynchronously. Why don't we do this if people are okay with this? I'm going to take a 15-minute break, and I'll be back at 12:45. I'll pick up from this point right here where I left off, and you know, uh, if you can come back, then you can continue. Otherwise, you can look at it later. Does that sound okay with people? I mean, again, I don't want to. Uh, I want to be sensitive to other professors that might be actually teaching. That you might be in other people's courses. I want to be sensitive to professors that are teaching at 12:45. So let me know in the chat if that's okay. If it's okay to take a 15-minute break right now. Okay, I'm getting people saying sounds good. All right, let me see how many people are in the chat. Still 9 people in the chat. Yeah, okay, guys. I think I need a break myself. And I'll just be back at 12:45. Okay. Um, and I'll continue with this problem. And again, if you want to come back, you can come back and watch me. Otherwise, you can watch it later. It's going to be a 3-hour long video, but I mean, I guess that's okay. You can always just like jump back and forth between these. Okay, so yeah, I'm getting thumbs up. All right, so I'm going to move. I'm not going to cut the live stream. It's actually going to continue, but I'm going to switch to the. I'm going to switch to my be right back and 15 minutes. So in 15 minutes, I'll be back, guys, and I'll continue. All right. Okay, let me see what's going on in the chat here. Hi, everyone. Ready for round 2? Okay, I don't know about you guys. Let me see how many people are watching. 6 people are watching. I'm running out of a bit of energy, um, but I think we can get done. Um, uh, get at least electricity done, or at least mostly done. We do have all of next week, so no need to rush. But let's continue with this problem. And let me switch to. There we go. All right, great. So this is the whiteboard where we left off, and just to remind you, this was our circuit, and the question number 1 was, what is the total capacitance of the circuit? And total capacitance, you look at the circuit, and you need to reduce two capacitors at a time, and so those two are in clearly in series, so you reduce them first, and we got to this. They reduced down to 18, and then these two, that one, this one, and that one, are clearly in parallel, and so we reduced those two and gave us the total, which was 23 nanofarads. Okay, the next part is a bit harder. Oh no, part B is easy. It's part C that's the hard one. Okay, so part B is what's the total charge accumulated by the circuit? Okay, and so the total charge, I mean, you don't have to worry about the charge on any one individual one. All three together are going to conspire to accumulate a certain amount of charge. And so this is just basically the definition that I gave you earlier of the capacitance. And that was question number 4, I think. Or number, yeah, this one right here. There we go. There's uh, the definition of capacitance. Okay, and I'm actually asking for the charge accumulated. So if I just multiply both sides by V, I'm going to get Q is equal to CV like that. And C we determined was 23 nanofarads. That's the total capacitance of the entire circuit. And the voltage I'm telling you is 100 volts, like that. All right. And so if you multiply the two together, you're going to get 2300 nanofarads, like that. Sorry, nanocoulombs, like that. And what I did was nano here is 10 to the minus 9. So I just carry the 10 to the minus 9 along like that. And you can write this as, if you wish, oh, 2300 times 10 to the negative 9 coulombs, like that. And if I move the decimal over, I can get 2.3 times 10 to the negative 6 coulombs. And that's just 2.3. 10 to the negative 6, what's that? It's micro. And so let me grab a little micro from up here. Here we go. It's micro coulombs. Okay, so that's the total charge accumulated. On the positive side of this whole circuit, like on this plate here plus that plate there, you're going to have plus 2.3 microcoulombs, and on the negative side, which would be that plate there plus that plate there, you're going to have negative 2.3 microcoulombs accumulated. Okay, so let's move on to part C, because this is the hard one. All right, and so what I'm asking here is, what is the voltage drop across each capacitor, and what is the charge on each capacitor? Okay, so you need to distinguish the total charge versus the charge on any individual capacitor. And you say, well, how do I do that? And the answer is, you kind of run the whole problem backwards. Okay. And Kaylin says, are you typing? I was, yeah. Uh, you're not. You're typing. It's not showing up. Oh, it looks like it's showing up now. Let me just ask. Is it working now? Oh, that's interesting. Hold on, I'll fix it. Let me see what's going on here. Something weird is going on. I have no idea what's going on. Part C. Well, actually, no. Let me see. Uh, oh, yeah, it is now. There was a very strange delay. I have no idea what was going on there. Okay. All right. Sorry, guys. Yeah. Well, uh, yeah, the internet. Okay. So let me get rid of the. Is it working now? And yeah. Okay. I'm seeing the my. Is it working now? Yeah. There's quite a delay. There's quite a delay. Okay. All right. Well, let's continue. Okay. So I was saying, how do we answer the question? What is the voltage drop across each capacitor? And the way to do that is you work backwards. We know that the voltage drop. So let me start with the combined. Okay, so when everything is combined, basically it's like everything is basically just one capacitor like this. Okay, and this capacitor here is just C123, and that's equal to uh, um, no, sorry, 23 nanofarads like that. Let me get rid of these here like that. Okay, so the voltage drop across the combined capacitance is obviously 100 volts because you got 100 volts on this side and you've got 0 volts on the other side. So that's the combined. Okay, so we haven't answered the question yet because I'm just starting from this one. Okay, so we can even say to the side here, voltage drop across C123 is 100 volts. Okay, now the next step down is we break these two apart and we're back to this one right here. Okay, so here we are. Now here's the trick. When you have two capacitors in parallel, the voltage doesn't split when you have things in parallel. So for this one, we can actually don't even worry about the numbers here. On this side, you have 100 volts. And on this side of the capacitor, you have 0 volts. Okay, why? Because if you trace the voltage here, this is at 100 volts, 100 volts, 100 volts. As long as you're just traveling along a wire, your voltage doesn't change. So you're 100 volts all the way up to that side of the capacitor. Okay, and if you follow this one, and again, if you're just following a wire, the voltage doesn't change. So 100 volts, 100 volts, 100 volts, and you get to here. Sorry, 0 volts, 0 volts, 0 volts. You get to here, 0 volts. And so the voltage drop across this capacitor is going to be 100 volts. But it's the same for the other one. Because if you follow this to there, and then you go down here, and all the way over to here, oops, all the way over to there, that's still 100 volts there, like that. Okay. All right. And over here, if you're following it this way, that's 0 volts, that's 0 volts, that's 0 volts all the way to there. And so you're at 0 volts there. Okay. Now, this one, I took it out, just to give me some space there. But this one here was the combined C12. All right. And this one was C3. Let me put some space in there like that. And so now you can say that the voltage drop across C12 is 100 volts. And you can say that the voltage drop across C3 is 100 volts. Okay? So when they're in parallel, the voltage doesn't split. Okay? When we look at resistors in a minute, current does split. But for voltage, when you have a split in your wire like that, right there, or you have a split there, the voltage doesn't split. Okay, so this is 100 volts all the way to there. It's also 100 volts all the way to there. And this is 0 volts all the way to there, but it's also 0 volts all the way to there. And so the voltage drop across C3 is 100 volts. That answers one of them, but it doesn't answer the that one right there. Okay, and so now we go to the next level down, and the next level down was this. Okay, all right. In other words, we're unraveling the whole problem. Okay, and whoops, I better grab the top part too. Okay, All right, great. Let's put another space in there. All right. Okay, so so now we're at this point. Now, we don't have to worry about C3 here because we know that that one has a voltage drop of 100 volts. Let's just worry about C1 and C2. So I'm actually, just going to remove this from the diagram altogether. Okay, and I'm just going to do that, and I'm going to do that. Okay, so and we know that at this point here, we're at 100 volts, and we know that at this point here, we're at 0 volts. But that doesn't tell you the voltage drop across C1, and it doesn't tell you the voltage drop across C2. What you can say is that the voltage drop across C1, let's write it that way, plus the voltage drop, across C2, okay? So the voltage drop across that plus the voltage drop across that, that's got to equal 100 volts, okay? But you don't know any one of them in particular. All right, so let me look in the chat here, make sure that everything seems to be working. Yeah. And oh, Aaron, so Tuesday's going to be final review. Yeah, yes, yeah, yes. Okay. All right, let me continue with the problem here. So there we go. We've got this drop there, and we got a drop there. Now you say, well, how do I get the voltage drop across that one and the voltage drop across that one? Okay, well, if you remember the definition of capacitance, it's this. Okay, whoops. And you can rewrite this to say that V is basically equal to Q divided by C, like that. Okay, now we're really working here with like a total C. So over here, what you can write is that this, for this V here, you can write as Q across number 1 times V, or divided by V1, plus Q over 2 divided by, not V, sorry, C1, like this. And over here, C2 like that. And that's got to equal your 100 volts like that. Okay? Now what? Well, the two Q's here, now this is a little bit subtle, but the two Q's have to be equal to one another. Q1 has to equal Q2. Why? Because the charge on C1 comes from C2. So whatever charge accumulates on C1 also accumulates on C2. So you could say that this is just this. All right? Like that. All right? And now you say, well, wait a sec. I'm sorry, we're trying to solve for the V's here. Well, this is true, but you know what, guys? That's not what we're actually trying to do. I apologize. I was heading towards the derivation. We actually want to solve for V1 and the voltage drop across C1 and C2. So we're just going to, let's get rid of this. I apologize. We're just going to use this as a check. Okay, so this is just a check. Yeah, I was solving a different problem. So over here, what you want is you want to say, well, V across C1. We still want the definition of capacitance. Where did I have it here? Well, I'll just rewrite it. We still want the definition of capacitance, and the definition of capacitance is Q divided by V, like that. Okay. So over here, if we rewrite this, we're going to rewrite this as Q divided by C1, like that. And you say, well, what's Q? Okay. And Q you can get by using this formula. C12 is going to equal Q divided by V across 1, 2, like that. All right. Now, do we have C12? We do. C12 over here, up here, was 18. All right. So where C12 is equal to that. Now, the reason this is the same Q all the way through there, okay, and I was heading down the wrong direction with this, but the reason it's the same Q is because whatever is accumulated on this capacitor is equal to whatever is accumulated on that capacitor, because one capacitor gets the charge from the other one. And effectively, you could say that the charge that's accumulated on on C12 is also the same charge, okay? And so we can actually solve for the Q from there and then plug it into here, and get that. All right. So what's Q? We get Q from that, where this is equal to 18 microfarads. Okay. And so here we can write Q is equal to C12 times V12. All right. And C12 we said was 18 nanofarads, like that. And the voltage drop across both of them is 100 volts, like that. And so we get 1800 nanocoulombs, or 1.8 microcoulombs if you want to put it in micro. But we don't have to, but we could. Okay, like that. All right. Now this is a bit subtle, and I think I was heading down the wrong path. So let me describe this again. This is just going to be a check. Okay, but we want that check because make sure we got it right. The voltage drop across C1, that's not going to be 100 volts. It's got to be less than 100 volts. The voltage drop across C2, also less than 100 volts. The voltage drop across both of them has to be 100 volts. Okay. You say, well, how do I get the voltage drop across just C1? Well, the answer is you could just use the formula for the definition of capacitance, which is this formula here. But I rearranged it. I isolated the V. So here's V, and that's got to equal Q over C, okay? And if I'm looking at only C1, then I want the charge on C1 divided by the capacitance of C1. But I didn't put Q1 here because the charge on C1 is the same as the charge on C2, and it's the same as the charge on both of them, all right? And maybe I should just mention that charges on C1, C2, and C12 is just Q, okay? And the reason is that like C1 can't get a charge except from C2, and so whatever charges, like if you lose an electron from there, then you have an extra electron there. If you lose 2 electrons here, then you have 2 electrons there. If you lose 100 electrons here, then you have 100 electrons there. And you just keep going on like this, and you realize, oh, the charge on that one is the same as the charge on that one. Well, if the charge on this one is the same as the charge on that one, then the two combined together have the same charge. Okay, so that's where that's coming from. Now, once you have that Q, then you can say, oh, okay, well then this is going to equal the, let's do it in this form like that, okay, 1,800 nanocoulombs, all right, divided by C1, and I forget what I called, what value I gave to C1, but let's go back up here. C1 was 30 nanofarads, okay, divided by 30 nanofarads here like that, and I get a voltage of, better be less than 100, so it's 18 divided by 30. It's 60. And the nano will cancel the nano, so you'll just have coulombs over farad, and a coulomb over farad is a volt. Okay. All right. Well, good. It's not 100. It's not over 100. Okay. So it should work out. Now, you know that the other one's got to be 40, because if this one's 60, that's got to be 40. But it should work out using the exact same equation here. The charge is the same because they're in series, like that. All right. But the capacitance is different. All right. And so over here we have 1800, but not divided by 30. I forget what C2 was. C2 was 45. Okay. And if I work that out, divided by 45 is 40 volts. And ta-da! Did that work? Did the check work? Yeah. Okay, it works. Okay. So, everyone good so far? Let me see here. Yeah, no other questions in the chat. Okay. So I think you can see why this is a little tricky. Just sort of remember this. When you've got two capacitors in series, Q on this one is the same as Q on that one is the same as Q on the effective. Okay. And so every place here, you don't have to say Q1 or Q2 or Q12 or anything like that. It's always the same Q. All right. And you just use this formula here, but just rearrange it. Rearrange it so that, if I multiply both sides by V, I get C times V is equal to Q. And then I divide both sides by C, I get that V is equal to Q divided by C. Okay, so we're going to use this, but we're going to use it twice. We're going to use it once for C1 and one's for C2. Okay, so if we use it for C1, you're going to get Q divided by C1. Again, it's the same Q for all of them. All right, and you say, well, how do I get that Q for C1? Well, the Q there is the same as the Q for C12. So if you use it in this form right here, just use, okay, put a little space in there so it's easier to see. Okay, if you use it in this form, you can find Q for C12. C12, 18 nanofarads, found that above. The voltage drop across both of them, 100 volts. That gives you the 1.8 microcoulombs, and that tells you how much charge there is on both of these. Great, so the voltage across C1, that's going to be that 1.8 microcoulombs or 1800 nanocoulombs divided by C1, that's 60 volts. Same thing for C2, and that's 40 volts. And so then you can go back to the check here, and they better add up to 100 volts, and they do. Okay, so does that answer the question? I think I had one more thing. I said, what's the charge on each of them? So what's the voltage drop across each capacitor? We answered that. And what's the charge on each of them? Well, the charge on each of them, we already answered too. So we could say, so the voltage drop across C1 is 60 volts, and across C2 is 40 volts, and the charge on both, and that's, I guess, the part that's a little subtle, okay, the charge on both is this number right here, okay, 1.8 microcoulombs. All right. So I have to admit this is by far the most subtle part of it, okay? And probably on a test, what I would do is I would walk you through this a little bit more, and I would say something like this. What's the potential drop across C12? And then I would say, what's the charge accumulated on C12? And as soon as I ask you what's the charge accumulated on C12, you would get that. And then I would ask, what is the charge accumulated on C1? And what's the charge accumulated on C2? Well, that's the same as the charge on both 1, 2, okay? And then I could ask you what's the potential across C1 and what's the potential across C2. And you can check that because the potential across one plus the potential across the other has to be equal to the potential across both of them. All right, so I hope that wasn't too much, and that finally answers that question. Okay, so let me see if there's anything in the chat here. All right. Well, you know what? You can just look at the timestamp, come back to this, and look at it a few times, and hopefully you'll get it. Okay. You're going to see something very similar with resistors, anyhow. All right. So let's go on with resistors. And what question am I up to? I'm up to question number 8. Okay, so here's question number 8 with resistors. And let's start off with just a simple question on the definition of resistors. And so I place a resistor with R equals, let's say 150 kilo ohms. Oh, let me get an ohm out of this. Omega. Copy, paste it in there. There you go. Nice. That looks good. Okay. In series with a battery of voltage, I don't know, what should we make it? 30 volts. What is the current in the circuit? All right, so this is exactly the gets at the definition of a resistor. If you put a battery in a circuit and you don't have any resistance, it's like a perfect wire, you'll get infinite current. Okay, obviously that can't happen in reality because there's always some resistance, but you know, if you really had a battery, a perfect battery, and you shorted it out with perfect wires, you get infinite current. So what is resistance? Resistance is what limits the current in a circuit. Okay, the bigger the resistance, the smaller the current for the same amount of voltage. The way you can think about this is voltage is kind of like a push. It's trying to push charges around the circuit, okay? And the resistor resists that, and the current is how much actually trickles through, okay? And so the law that governs this is actually Ohm's law, okay, and it is the definition of resistance. It's V is equal to IR, or another way you might see that written is R is equal to V divided by I, okay, like that. All right, so uh, let's just solve this problem here. I'm asking for the current, or you know what? Maybe another way to think about this. Maybe this is a better way to think about this. Yeah, like that. Okay, let's I want to make sure you have the right intuition here. If you just look at I is equal to V over R, V, the more push there is, the more current is going to get through. Okay, so the more push there is, the more current there's going to get through. But the bigger the resistance is, the less current is going to get through. So that's why the resistance is in the denominator. Okay, so that's what this is about. And actually, that's the form that you wanted in to solve this problem. And so the voltage I said was 30 volts. Okay, and the resistance I said was 150 kilo ohms, like that. Typical lab size resistances are kilo ohms. Human tissue, you're going to get up into mega ohms, okay? And you do want to know about human tissue because there are some therapies that make use of electricity, and you want to, so well, how, if I put so many volts across this tissue, how much current am I going to get? And hopefully you don't put too much current across someone because current, high current can burn, or well, if it's across the heart, it can damage. Okay, so anyhow, what's this work out to? Well, first we got to convert to the kilo to 10 times 10 to the 3, like that. Okay, and let me just work that out on the calculator. So this is 30 divided by 150 times 10 to the exponent 3, like this. And that's going to equal this number here. And the units are amps, okay? And how many decimals do I want to move this over? If I move it over 1, 2, 3, so I get 0.2, that's milliamps, like that, okay? And that's a typical, a smallish but typical size current in a lab. All right, let me see here. Any questions in the chat? Nope. All right. Well, there you go. There's the definition of resistance. And you know what? The next thing is what happens when you put resistors in series and in parallel. And so what I'm going to do is I'm just going to go up here and I'm going to copy and paste the capacitor problem. Okay. And I'm actually going to use the same numbers, but of course convert to the other units. Okay. All right. So part A here. We have a resistor R1, which is a 16, let's do kilo ohms, 16 kilo ohm resistor, okay, in series with a R2 equals 32 kilo ohm resistor. What is the equivalent resistance? And the answer is, what happens? Well, with capacitors, it's way up here. Here's the rule with capacitors. Capacitors in series, the reciprocals add. But if you have resistors in series, they just add. Okay, so they're kind of the opposite. And so here you have R. Whoops, I shouldn't have called this C1. Oh, well, I'm in the wrong spot here. There we go. Okay, so R equivalent is equal to R1 plus R2, and that's going to be 16 plus 32 kilo ohms, and that's going to equal 48 kilo ohms. Okay, that was easy enough, right? All right, and now same question. But in parallel. All right, and resistors in parallel, the reciprocals add. All right, and so there you've got basically the formula 1 over R equivalent is equal to 1 over R1 plus 1 divided by R2, like that. Okay, And you know what? I can just well, I can do this very quickly on my calculator. It's easy enough. I don't think I need to show you how to do that on a calculator. It's 1 divided by 1 divided by 16 plus 1 divided by 32. That's that 10.7. 10.7. And since we're working in kilo ohms, everything's in kilo ohms. The answer will come out in kilo ohms. Well, actually, I should do this. R equivalent is equal to 10. Okay. So I hope that was easy enough. All right. Any questions in the chat? Nope. All right. So let's now do the same kind of problem as this, okay, as this one here, where we have several in a circuit, but let's do them with resistors, okay? And I'm actually going to grab this one off of my the picture off of the website, and hopefully this picture will just cut and paste over. Not quite. It's question 10. Okay, and let me fix up the picture. Almost there. There we go. Okay, and let me change the numbers. In fact, you know what? Let me use the same numbers as I did for the capacitors, but of course, switch them over to resistors like this. So make this one 30 kilo ohms, make this one 45, and make this one 5, like that. And well, there's our circuit. What am I asking? Well, I'm going to ask the following questions. Okay, what is the total resistance of the circuit? What is the total current drawn by the circuit? And what is the voltage drop in current through each resistor? I think if you look at this problem and you compare it to question number 8 here, which we can do right now. Okay. What is the total capacitance of the circuit? What is the total charge accumulated? What is the voltage drop across each capacitor? And what is the charge on each capacitor? Compare that to here, and you'll see that it's the same kind of question, only instead of total charge, you're talking total currents. And instead of like individual charges on each capacitor, it's currents through each resistor. Okay, so they're really very similar problems. But of course, when we're doing this particular problem here, we don't make use of the definition of capacitance. We make use of Ohm's law. Okay, and I think conceptually this one might be a little bit easier to see, but let's go through it. Okay, and in the meantime, let me also, since I'm going to put this online, I might as well get my little ohm symbol in there. All right. So what is the total resistance? Well, same thing. You have to reduce these, and you reduce these two first. And so you could say R12. So this is the answer to part A. Okay. R effective, sorry. Yeah, R12, which is the effective for 1, 2, is equal to R1 plus R2 like that. And R1 is 30 kilo ohms, and R2 is 45 kilo ohms. And so the total equivalent is going to be 75 kilo ohms, like that. All right. And so now what does this circuit look like? Well, now this circuit is reduced to, oh, you know what? Instead of 15 volts, let's do 100 volts. Why not? Just like the previous one. Okay. So same numbers, but different units for the different electronic devices. Okay. So that's part of the way to the answer. Oops. So this has now, that circuit has now been reduced to R12, where R12 is going to be a combined circuit here like this. Okay, or sorry, combined resistor like that. Okay, how's that so far? Okay, so that's step number 1. We combined R1 and R2 into R12, and now that resistor and that resistor are in parallel to one another. This one, let me put in the numbers so you can see the numbers that I'm going to use. This one is the 75 kilo ohms that we just calculated. And this one here is, what did I say that one was? 5 kilo ohms. Okay, like that. All right, now these ones are in parallel, and so 1 over the effect of all, the equivalent of all of them is R, I'll call it R123, like that. And that's going to equal 1 over R12, which is this one, plus 1 over R3, which is that one. Okay, I hope my notation isn't confusing. When I say R123, that means all three of them combined into one, and R12 just means just R1 and R2 combined, and R3 is all by itself. Okay, well, I think you can do this on your calculator, so I'll just give you the answer. It's going to be 1 divided by 1 divided by 75 plus 1 divided by 5. And it looks like 9 kilo ohms. Okay, there you go. And that answers part A. So the equivalent resistance is this. All right. See if there are any questions in the chat. Nope. Looks good so far. And looks like everything, the delay problem isn't showing up. Okay, I see my stuff there. Okay, well, okay, so part B, what is the total current drawn? Well, for the total current, you just use Ohm's law, but you apply Ohm's law to the entire current, to the entire circuit. Okay, so apply. So when you say that, you say, well, what do you mean by that? Apply it to the whole circuit. Okay, well, this V, that's the V that's like globally there. We'll say, okay, and the R, that's going to be your global R, or your equivalent R, which is this, and then you can find the current. Okay, so you got the current is going to equal V divided by R, where R is the equivalent R for the whole circuit. In other words, R123, which we found to be this. Okay, well, I think it's pretty easy now to see that I is going to be 100 volts. Okay, so it's like imagine the whole thing, you know, is just one resistor. In fact, I can draw it here. Okay, it's worth drawing it very quickly. Okay, let's get rid of this. Let's get rid of that. R123 is going to equal 4.69 kilo ohms. Okay, so basically that entire circuit just reduces to this. Okay, and so if you ask the question, what's the current through there? Okay, well, there can only be one current, and that's going to be I, like that. That's going to be 100 volts push, and with a resistance of 4.69 kilo ohms, like that. And then, of course, the kilo ohms here. Oh, why can't I cut and paste? Copy, paste. The kilo ohms we want to write as times 10 to the exponent 3, like that. And what does that work out to? 100, whoops, 100 divided by 4.69 times 10 to the exponent 3 turns out to be this, and that's in amps, or if you want to write it as milliamps, 21.3 milliamps, like that. Okay, so that answers that one. All right, now again, here part C is the difficult one, is what's the voltage drop across each resistor. Okay, this is kind of, and current. Okay, this is kind of like what's the voltage drop and charge on each of the capacitors. You run the whole problem backwards and apply Ohm's law at each point. Okay, so in the previous one we ran the problem backwards and applied the definition of capacitance at each point. Here we'd run it backwards and apply Ohm's law at each point. Okay, and so we've kind of already started with this, because now we know that I is going to be that. Okay, now the next step back is this one. All right, that one. So here's part C. All right, now what's going on here is you could say, okay, I know the current here is 21.3 milliamps. Okay, we know the current there is that. All right, but what happens to the current at that point right there? It splits. Okay, and so, sorry, that's my dog barking at something. Okay, so that current splits. Okay, and so over here what you can say is, you could say, okay, the current going through 1, 2 plus the current going through 3, resistor 3, that current has to equal 21.3 milliamps. All right, I don't know, and that's going to be our check. I don't know the current going through R12, and I don't know the current going through R3, but I know that the sum of those two currents has to equal 21.3 milliamps. Okay, the voltage doesn't split here. Why? Well, because that's 100 volts all the way to here, and that's also 100 volts all the way to there. Okay, and this is 0 volts all the way to there, and it's also 0 volts all the way to there. Okay, so when a wire splits, the current splits, but not the voltage. All right, and so now you could say, so what's the current? What's the current through R3? All right, well, what's the voltage drop across R3? We know that it's 100 volts. Okay, and so we can apply Ohm's law here like this, but we can apply Ohm's law just to R3 like that. The V there, I'll just leave it as V because it's the same across both of them. It's at 100 volts. And so over here, I've got the 100 volts, which is the voltage drop across R3, divided by R3, which is 5 kilo ohms, like this. And that's going to equal 20 milliamps. All right, there's your I3. And so now we could do the same thing for I12. What's the current through I12? And the current through I12 is the same formula here like that, but now it's the resistance, the equivalent resistance of 1, 2, like that. And that's going to equal this, but it's 75 kilo ohms. All right. And if you take 100 divided by 75, you get 1.33, 1.33 milliamps. And does our check work? Well, if you do 20 plus 1.33 milliamps, that's going to equal 21.33 milliamps, and it works. Okay, so I agree these are kind of subtle, but you know, it's kind of like important to understand what's going on here. When you get to this point of the junction here, you know, you got that split. You're looking at potential and current. Potential doesn't care about splits. 100 volts all the way to there, 100 volts all the way to here. Okay, but when you get to a junction, current splits. Okay, so that 21.3, some of it goes down this way and some of it goes down that way. If you add up how much goes down here and how much goes down there, the two together have to add up to 21.3. Okay, and as you might expect, the smaller the smaller resistor actually has the more current going through it. And so that one actually has 20 milliamps going through it, and this one only has 1.33 milliamps going through it. Okay, now how do you work this out? Well, you just do one at a time. You look at that and you go, okay, I know that the potential drop across that one is 100 volts. So if I know the potential drop across it is 100 volts, and I know the resistor is 5 kilo ohms, then I know the current through it is 20 milliamps. And the same thing here, even though this is an equivalent resistance out of two of them, You know that the potential drop across the equivalent is 100. You know that the equivalent resistance is 75, so that gives you 1.33. And you say, well, is this right? You can do this little check. You could say, well, the current here splits. I get so much going down this way, so much going down that way. Do the two have to add up? 20 plus 1.33, that's 21.33. And here I only had 21.3, and that's just because I rounded off. In fact, if I go back here and I just kept another decimal, it would be this, and and then it works out. That works out perfectly fine. Okay, and so are we done? Well, not quite. We've got the current through that one, so now we can conclude. So we know the voltage and current through R3 is 100 volts and um, 20 milliamps respectively. Probably not the best way to say it, but the voltage across it is 100 and the current through it is 20 milliamps. Okay, so are we done? No, we have to go back one more step and break up R12. Okay, and so now we can take this diagram here, all right, because that's one step back. And now the current here, just that I12, that's going to be 20 milliamps. Oh, this looks terrible. Hold on here. I'll get the diagram right. Okay, and the current through this one, might as well draw both currents in there. This one is I3. That one was the 1.33 milliamps, like that. Okay. All right. So this is the diagram so far. Okay. Well, we've answered the question for that one, potential drop of 100 and current through at 1.33. What about this one? Well, for this one, what we have to do is just concentrate on this piece right there, okay? So we just have to concentrate on that and this, okay, because we got the other piece of it, okay? And you say, all right, well, now what? Well, what's this actually equivalent to? It's actually equivalent to all the way back here to this one. So we're going to split up R1 and R2, okay, like that. All right. Now, still the same current through there. Let's see if I can draw this quickly. All right. Still the same current going through there. But now, what are those two? I forget now. R1 is, R1 was 30 and 45. Okay. So over here, we have this one is 30. And that's kilo ohms. And this one was 45 kilo ohms. All right. Still looks kind of ugly. There we go. Okay, let's look at that. Okay, so what did I do here? What did I do here? Basically, I just concentrated on this part of it. Okay, we know that the potential drop across this top part here is 100 volts. So here we got 100 volts. We go down to 0 volts. Okay, we know that the current through just this portion, okay, like after the split, is 20 milliamps. Okay, so there we got the 20 milliamps. Okay, and we know that this R12 is made up of R1 and R2 in series. Okay, and now the current doesn't split because there's no split in the wire, but the potential does. Okay, because you're jumping across two electronic devices here. Okay, and so like you've got two different situations. When the wire splits like that, the voltage stays the same on both sides, but the current changes. But when you have something in series, the current stays the same. The current is the same all the way through this, but the voltage splits across each piece. Okay, and so now you can say that there's going to be a voltage drop across R1, and there's a voltage drop across R2, and that's got to equal 100 volts. That's our check. Okay, we're not going to use that to solve it. That's just going to be our check. And now you go, well, how do I get the current? How do I get the voltage drop across this one? And how do I get the voltage drop across that one? Ohm's law. So all the way back to here, but not in this form, in this form. Okay, so we're going to use Ohm's law. So what is the voltage drop across R1? Well, we can call it, well, we did call it VR1 like that. That's going to equal I12. It's the current that's forced through R1. Okay, that multiplied by R1. Okay, so again, the current through both of them is at 20 milliamps. There it is. And that one there is the 30 kilo ohm. And so 20 milliamps being forced through 30 kilo ohms is going to be, well, milli is 10 to the minus, you know what, I'll write it out, okay? The milli and the kilo kind of cancel one another out, but I'll show you that, all right? Paste. So the milli is like what? It's like times 10 to the negative 3. And the kilo, what's that? That's like times 10 to the positive 3. And so the 10 to the minus 3 and the 10 to the positive 3, they cancel. And so you get, is that right? 20 milliamps. Hold on here, 20. Why am I getting 600 instead of just 60? I'm making some mistake. It should be 60 volts, but I'm not sure what I'm doing wrong here. Let me see. Did you see what I might be doing wrong in the chat, guys? It should be 60 volts, not 600 volts. Well, you know what? Let me do the next one too. Here, V is equal to IR. So we got 20 milliamps. And what were the two resistors equal to? 30 and 45. That's right. 30. And so the next one will be 45. Milli is 10 to the minus 3, 10 to the 3. Oh, I'm doing something wrong, but I'm not sure what. Let me just see here. So we got 100. Oh, I know what I'm doing wrong. I'm so sorry, guys. That's not the 20 milliamp. That's the 1.33. That's the 1. I picked the wrong current there. Okay, I apologize. All right. Okay, yeah, that's what happened. This branch here, that's the 1.33, and this one was the 20 milliamp. Okay, so that's what I did wrong. And let's see, did I make that mistake elsewhere? No, I didn't. Okay, so I accidentally just copy pasted it from here. So get this lined up a little bit better. Yeah, the top one with the higher effective resistance is 1.33, and the bottom one with the lower resistance was 20. Okay, so yeah, this number here is incorrect. That's 1.33, and that's 1.33, and that's 1.33 here, and that's 1.33. Okay, and so over here, that's not 600. That's going to be 30 times 1.33, and that's going to be 40. And this one is going to be 60, and now I'm happy. All right, so the check, it works, right? So that should be R1, R2 here, like that. Okay, the check works out. Okay, so because 40 plus 60 is equal to 100. So R1 has a current of 1.33 milliamps and voltage drop 40 volts, and R has same current but a voltage drop of 60. All right. Okay, yeah, long problem again. Like on a test, I would walk you through this. I would, make sure that you had this, and then would say, okay, what's the current? What's the voltage drop across both of them? What's the voltage drop across just one of them? What's the voltage drop across both of them? And what's the sum of the two voltage drops? And so that you basically this entire piece here would be broken up into several pieces. Okay, let me look in the chat, see if there are any questions. All right, no questions, and we're down to the last of um, the problems with electricity and magnetism. So, what question is that? I guess we're up to question number 11, like this, and these are the RC circuits. Okay, the RC circuits. All right. So, let me just see what I gave you for an RC circuit here. I gave you this. I could do something similar to this, but we'll move it, or we'll change some of the numbers. I don't know. Let's do a 30 kilo ohm is fairly reasonable size resistor, and let's do a nanofarad capacitor, and let's do what the heck? Let's do a 9-volt battery. Actually, you know what? Let's do 47 because you can actually buy a 47 nanofarad, and for the resistor, let's do 45. You can actually buy these sizes, okay? And 9-volt battery, well, you have a 9-volt battery, and you put it in a switch. You close the switch, the capacitor begins to charge, okay? And what's the maximum charge that will accumulated? And what is the charge on the capacitor? Well, I don't know after how many seconds, so I may have to change that in a minute. Let's just get the let's do one at a time. So um, we'll change this because it's going to change the time constant. Okay, so basically, let me give you the theory first before I jump in and start solving this. Basically, you have two situations here with an RC circuit. You can maybe write this here. If you've got an RC circuit with a battery in the in series, what happens is the battery is supplying the energy which charges up the capacitor. Okay, now the battery, if there were no resistor, the battery could deliver all of the current that it needs to charge up that resistor instantly. Okay, not physical. That doesn't naturally happen. Okay, there's always some resistance. Okay, the bigger the resistance, the longer it's going to take the battery to fill up the capacitor. Okay, so yeah, this is charging up, but it's charging up over some period of time. And so in this case, with the battery in series, the capacitor charges up. And the formula here for this case is going to be Q as a function of time, that's the charge on the capacitor, is equal to Q naught, that's a maximum, and it's going to be 1 minus the exponential of minus t divided by tau. And I can actually get the tau because I have this ready, tau. There we go. It's this. It's the Greek letter for t, but it's got this kind of scripted. Okay, there you go. Right. Or maybe here's another way to do this: e to the exponent t divided by tau. Okay, on your calculator, this is just the letter e. It's that Euler's constant. Okay, now this is when it charges up, and the thing is I said that Q naught was the maximum, and you say, well, what is that maximum? How do you calculate it's Q naught is equal to C times V. Okay, where C is the size of the capacitor and V is the voltage. Now, what if you have RC with no battery? Okay, if you've got RC with no battery in series, the capacitor discharges. So the capacitor might be prepared with some charge on it, and you just short out the capacitor. Now, if there were no resistance when you shorted it out, it would instantly discharge. But if there's some resistance, the resistance resists the current that allows for the discharging, and you get the same formula, but it's not 1 minus, it's basically this one. It's exponential decay like that, okay? So there's the two formulas, and that doesn't look too bad actually. All right, now what? Well, you need a couple of things. You need that tau, all right? And well, I guess first you need to decide, do you use that one or that one, okay? And then you need the tau, all right? And for both of these, tau is the characteristic time constant. It's just equal to R times C. Remember, the bigger the resistor, the longer it takes to charge up. The bigger the capacitor, the more charge it can accumulate, the longer it takes to charge up, okay? The size of the battery doesn't affect how long it takes to charge up. The size of the battery only affects how much it charges up to, like the maximum charge, but it doesn't affect the rate at which it charges up. Okay, so great. Now this one I have it charging up, which is like what I have online. I guess it's okay. I mean, we're going to use this formula right there. Okay, it's the harder of the two to work with. Okay, so we put a 45 kilo ohm resistor in and a 47 a nanofarad capacitor and a 9-volt battery, and we switch it on, and the capacitor begins to charge up. Okay, what's the maximum charge that will accumulate on the resistor? On the resistor, geez, on the capacitor. All right, so what's the maximum charge that will accumulate on the capacitor? That's this equation right here. That's the maximum charge, okay? And so that's going to equal the 47 nanofarads like this. Remember, nano is 10 to the minus 9. And the voltage I said was 9 volts like that. Okay. And so this is going to equal, we can just carry the nano along. And so this is going to be 47 times 9. And it's equal to this. Okay. There's the nano that I just carried along. And then farad times a volt. The farad times a volt is a coulomb. And so this is going to be 423 nanocoulombs. Okay, that's the maximum charge that this capacitor will accumulate. Okay, now it will take not a long time, but I mean it'll take time to accumulate to that. It'll never get over this amount, but it approaches it from below. Okay, let me see if there's any questions in the chat. All right, good. And now the next thing is, so I did this with those other numbers. Let me see what the time constant is, because we're going to need it in a minute. So maybe I could do a part B here. We'll call this part C. What is the time constant? Okay, and that's tau is equal to RC. That formula right there. And R is equal to 45 kilo ohms. And C is equal to 47 nanofarads. And what's that going to equal? That's going to equal, well, first, let me convert this all to MKS. So that's times 10 to the 3. And nano is times 10 to the minus 9. Okay. And so that's going to equal, well, I'll work it out. 45 times 47, okay, times 10. So I just multiplied 45 times 47, and now I have times 10 to the 3 times 10 to the minus 9. So that's 3 minus 9, so that's 10 to the minus 6. And so, and the units are actually seconds. Okay, they'll actually work out to be seconds. And so that's this many microseconds. And oh, let me go grab a micro from somewhere. I'm just cutting and pasting. That's why I'm scrolling up here, guys. Sorry about that. Do I have a micro anywhere? There we go. There's our micro. Microseconds. Or you can actually write that as, because if you move the decimal over 3 more, 2.115 milliseconds. Okay, do that. Okay, there we go. All right, now a millisecond, I mean, you know, for humans that's pretty fast, but for something like an oscilloscope, you know, that's only a thousandth of a second. I mean, think about it this way: your computer runs in at gigahertz speed. So that's a billionth of a second, okay? And so that's about the limit of our circuitry. We can measure down to a billionth of a second. That's 10 to the minus 9, okay? And here we're only at 10 to the minus 3. So there's no problem measuring that level. So you know what? Instead of doing 10 seconds, how about 1 millisecond? How long does it take to get to 2 milliseconds? How long does it, what is it, sorry, what is the charge in the capacitor after 1 millisecond, after 2 milliseconds, after 3 milliseconds? And we don't have to go further. I think that's enough, okay? And so, well, let's answer the question, all right? So what's the charge in the capacitor after 1 millisecond? Well, here is the formula for charging up, okay? So here we go. There's the formula for charging up. And we want the charge. So we actually want to solve for Q of t. Okay, so that's Q as a function of time there, like that. Okay, and so what's that going to equal? That's going to equal, for, let's do 1 millisecond. That's going to be equal to the maximum charge. And we determined that the maximum charge was going to be 423 nanocoulombs multiplied by 1 e to the exponent. All right, so negative, so what's t? Well, we waited 1 millisecond, so there's 1 millisecond, okay? And divide that by tau, the time constant, 2.155, or 115 milliseconds, like that, okay? Notice that both t and tau have to be in the same units here. So milliseconds will cancel the milliseconds. All right, so actually I could just write that on the next line here. Just so when you look at this later, you know what I did. The milliseconds here, we'll just simply divide out the milliseconds there, like that. Okay, and it's just a matter of plugging this into your calculator. Let me do it in a couple of steps so you can see how this works out. So this is going to be e to the minus 1 divided by 2.115. So where's my e? There it is. That's Euler's constant. 1 divided by 2.11. Whoops. All right, and that's this number right here. All right. And if we just crunch that through, now the rest of this is kind of easiest, so I'll just give you the answer. 1 minus that, multiplied by 423. So I'm getting 159 nanocoulombs after 1 millisecond. Okay, so if you had your oscilloscope on and you say to the oscilloscope, you have a trigger at as soon as you close the switch at 0 milliseconds, after 1 millisecond, your oscilloscope would say, oh, I'm measuring a capacitance of 159, or a charge of 159 nanocoulombs. Technically speaking, oscilloscopes do not measure charge directly. They measure voltages. So you wouldn't measure the charge across the capacitor. You'd be measuring the voltage across the capacitor, but then you can work from the capacitance, the known capacitance, you can get the charge on it. Okay, well there it is for after 1 second. We could do the same after 2 seconds, or 2 milliseconds, sorry. So put that, actually we could just say here equals 2 milliseconds, and over here we can say at t equals 1 millisecond, like that. So same thing, but now we've got a 2 in there, and I'll just give you the answer. That's going to equal, all right, so that's 1 minus Euler's constant to the negative 2 divided by 2.115, and multiply that by 423. So I'm getting this number here. Let's round it off. Nanocoulombs after 2 milliseconds. Okay. And what the heck, one more. After 3 milliseconds. And what's that going to equal? So, see if can I edit that? Oh, good. All right. So you can see that what's happening is it goes from 0 nanocoulombs to 159 nanocoulombs to 259 nanocoulombs to 321 nanocoulombs. And if you wait long enough, it'll eventually get to 423 nanocoulombs. So what's it doing? It's starting from no charge. It's building up, building up, building up, building up until it finally gets to the maximum charge like that. Okay, um, we're actually done with everything in electricity. So let me see what's going on in the chat here. And you know what, guys? I think I said I was going to go till 210, but I don't see a point to start magnetism right now. So I think we can just say um, call it quits for this. But basically, I've gone through everything that we can possibly do that I would ask you with electricity. Okay, so let me just wait in the chat a little bit, see if there's any questions. So, Aaron, you're asking, so Tuesday is going to be the final review session, correct? Yes, Tuesday is going to be the final review question. It'll be on magnetism. There's a little less on magnetism, and uh, uh, I won't do all, like, there's a whole bunch of possible things that you could do with inductors. I don't think it's important to do them all. Inductors are not as important for people in biology as capacitors and resistors. Okay, like, we talk about the capacitance of tissue. You could actually look this stuff up, and capacitance and resistance of tissue. Inductance a little less. So I won't do a lot of problems with inductance, but there is a couple of things with inductance that could eat up a lot of time. But probably about an hour on the magnetism stuff, and then another hour on the optics stuff, and that'll be Tuesday, and then we'll be ready for the exam on Friday. Okay, so is that okay with everyone? I'll just wait a few seconds to see what you guys say in the chat. Call it quits, guys. Yes or no? No. The exam for physics 112 has to be on the Thursday. Okay, and because I gotta make it align with when you guys are available. So I think I emailed this, and uh, I don't remember now, but I think the exam for Physics 112, I'm going to start it at 11. But even if you're in the section that starts at 12:45, you can start it at 12:45. You're going to get 3.5 hours no matter when you start it, okay? And that'll be Thursday, okay? The exam for Physics 102, I don't know if I have any 102 people in the room, but if I do, the exam will be on the Friday, okay? So there's only 4 people here. I'm seeing one okay, and if there's no other questions, guys, you can always email me. You can always catch me Google Hangouts in the evenings. So there we go. Okay. All right. I'm gonna end this live stream. Bye bye, everyone.